Hello, and welcome to the first episode of The Science of Dr. Stone. This little YouTube series is meant to be a sort of companion piece to the Dr. Stone anime, where we'll look in depth at the scientific principles and theories demonstrated by Senku. Now, 2 points before we begin. First, we're going to go in chronological order of the events of the anime as opposed to pure episodic order. So what that means is we will start with episode 5 and then jump backwards to episode 1 and then move on from there. Point number 2, this series will contain absolutely zero spoilers from the manga. The reason being is because I haven't read the manga. So please do not provide any spoilers of events that haven't happened in the anime in the comments below. Without further ado, on with the episode.
Surprisingly enough, there are quite a few animals that use tools. Crows, otters, orangutans, and more. But out of all the creatures in this world, only one can make use of science. When cellulose is heated through friction and exposed to air, it rapidly oxidizes, giving us combustion.
Fire really is one of the foremost cornerstones of human civilization. Without it, our ancestors wouldn't be able to cook their food, keep themselves warm in cold weather climates, or keep fierce predators away at night. But fire is just so much more integral to human civilization than that. In fact, some historians and anthropologists believe that if it wasn't for fire to cook their food, our ancestors wouldn't have been able to fully develop their brains to develop much more advanced forms of civilization and culture. Honestly, it comes as no surprise that one of the first scientific principles Senku explores after depetrifying is fire. Now, if it sounds like I'm overreacting, I'm really not. With fire, you can keep yourself warm at night, scare away predators, use it as a signal for others in the area, cook food, boil unclean or salty water, survive in cold weather climates, cauterize open wounds, smoke as a bug repellent, use a light to see in the darkness. So with all that in mind, I think it's pretty safe to say that fire is fairly important. But what is fire? So the first thing that we need to understand is that fire is a consequence of the chemical reaction known as combustion. So all fires result from combustion, but not all combustions result in fire. So let's start with the more general principle of combustion then. Combustion is a rapid exothermic redox chemical reaction. Now, exothermic means that there's a net amount of energy that's released from the system. So more energy comes out than that goes in. Redox is short for reductant oxidant. This signifies that in the chemical reaction, one element's electrons get transferred to the other element. The oxidant actually loses electrons and the reductant gains them. So now you might think that this definition is fairly broad. Does that mean all exothermic chemical reactions result in combustion? No. And that's why there's a key word in this definition, rapid. So the key difference between an exothermic redox reaction and combustion is that combustion fuels itself. Once you get combustion going, it'll create a chain reaction and will keep the chemical reaction going. For those of you who are more chemically inclined, you'll probably notice this is fairly different from most other chemical reactions, like synthetic reactions, where you have to constantly put activation energy into the system, even though it's exothermic. Alright, now let's get into some of the examples of combustion. So the first thing that we need to know is that there are two forms of combustion, complete combustion and incomplete combustion. Now, since complete combustion is one of the steps required to have incomplete combustion, it makes more sense to focus there first. Probably the easiest example that we can start off with is hydrogen plus oxygen give us water. Let me just balance this really quick. There we go. So what's going on here? Well, we have a concentration of hydrogen, we have a concentration of oxygen. Now, the reason why we have H2 and O2 is because the atoms are more stable this way. Now, what do I mean by that? Well, if I take just a simple, let's start with just a simple hydrogen atom, right? You have the hydrogen atom, it's got a proton and it's got an electron, and we can say that this is its orbital. Now, it's whizzing all over the place, right? It's going this way, it's going that way. It's going in just about any direction, right? Now, if we introduce a second hydrogen atom, we will see that the proton from this atom attracts this electron electromagnetically, and vice versa with this proton and this electron. So the two elements are going to attract. And the reason why there's a net attraction is because the electrons are in constant motion, right? If the actual arrangement looked something like this, and the elements were stationary, there would be a net repulsion here, right? Because the negative charge from the electron and the negative charge from this electron will push each other away. But because they're constantly in motion, the net polarity, the net negative charge from the electrons is going to be weaker than the strength of the protons. And since they're farther away than how the electrons get, this is a very small diagram. These are actually like a lot of space between the two. Because this gets a lot closer to the proton than the protons are, there is more attraction than the protons repel each other. So what ends up happening, let me redraw this, clean up a bit. So what ends up happening, here are the two protons, the electrons end up being shared between the two atoms. So we have the one electron here, and the other electron here, but now the orbits actually go around the entirety of the two protons. So like this electron might whiz around that proton, and this one might whiz around that way, and might continue orbiting, but then might go that way, and this one might orbit around this one. And basically, what happens is each electron will now orbit the protons of the other atom. This is called a sigma bond, and it's one of the strongest bonds that is created in chemistry. Now this sigma bond stays stable, again because of the electromagnetic attraction between the protons and electrons. And once this bond is formed, energy is released. This happens also due to electromagnetism. The two electrons, as we noted, repel each other, but repulsion is not strong enough to cause a separation between these two elements. What's going to happen is that when these two electrons get closer together, they're going to force a change in direction, a change in momentum, and that's going to reduce the electrons' kinetic energy. Now, kinetic energy doesn't just vanish, it gets transferred into electromagnetic energy, light. We'll look more into that later. Now, as you expect, a similar process occurs in oxygen, except that the atoms are double bonded. So let me draw the orbitals. Oxygen's kind of similar. There's a general principle that's happening that's basically the same, except since it's oxygen, it's a little more complicated. So I'm going to draw up two oxygen atoms. Now, we saw that the hydrogen atom, right, it had a shell that was literally a sphere, like a full sphere that went around the proton. Oxygen is a little different. So we have the protons in the center. There should be 8 of these guys, but they're all kind of concentrated in the center, right? The protons' outermost p orbitals are going to look a little something like this, right? They're going to kind of come out and form kind of a shape that kind of resembles that. And so here's another one that's going to be nearby. There's the protons there. So similarly to before, the protons are going to attract the nearest electrons that are nearby, and vice versa, right? There's an electromagnetic attraction that's going to bring them together. And how that ends up, and then what happens as a result, you get a double bond between the two atoms. So first, we have a sigma bond between two of the p orbitals. So it's going to look a little something like this. So here's one proton, here's the other proton. Now its p orbital is going to kind of engulf the other one, and then vice versa. So it's kind of gonna look like almost like this, right? So they're gonna overlap. Usually it's not drawn this way, but I want to signify that this is a sigma bond, so that means that the electrons are going to orbit around the proton of the other atom. Now, the other orbitals don't connect, but we also have what's known as a pi bond that forms. So we have one other p orbital, and what's going to happen here is that they're going to meld together and form what's known as a pi bond. So the electrons that fly around in these orbitals, they're now going to swap and go into the other orbital. Now, to clarify, they're just going to lap over into the other's p orbital. They're not actually, like, this electron is not going to whiz around this proton and vice versa. That's why pi bonds are generally weaker than sigma bonds. Now let's get back to the combustion reaction. First, we add some heat to the system to get things going. Without heat, nothing will happen. Even if there's a large concentration of hydrogen and oxygen, there will be no reaction unless we add some activation energy. Now this is going to be true for all chemical reactions except spontaneous reactions. Now when we add heat, what we are doing is we are returning the kinetic energy that was originally converted when these covalent bonds first formed. The heat causes further propulsion and torque in the electrons. This allows them to get as close to the other electron as much as possible, that we get maximum repulsion, and this is going to be strong enough to actually force the break of the sigma bond. Now once the sigma bond is broken, the atoms are now free to move around and then collide into other atoms, which then causes further breaks in sigma bonds, and that's going to ultimately spark a chain reaction. We can imagine what's happening here with the start of a game of pool. You can think of the covalent bonds as the neat and ordered lined up pool balls, and the cue ball being the activation energy that starts the chain reaction. Now once all the bonds have been separated, these free atoms now once again find themselves attracted to one another. However, the hydrogen atoms are going to find the oxygen atoms far more attractive than other oxygen atoms. The reason why is because the singular proton of the hydrogen atom is going to be overwhelmed by the electromagnetic attraction of oxygen's 8 electrons. Even though the electrons are in constant motion, the individual p orbitals, which each contain 2 electrons, are still twice as attractive as hydrogen's single proton and electron. And so 2 hydrogen atoms are going to come together and attach themselves to the p orbitals of the oxygen, and this is what creates water. Now just as before, there's going to be a drop in kinetic energy which is transferred out into photons and heat, which sparks other atoms to break up, and then we continue the chain reaction forward. So that first example contained a pretty in-depth look at chemical bonding, but it's important that we understand the fundamentals of what's going on here, because this will serve as a baseline for future episodes. Dr. Stone contains a lot of chemistry. So moving on from hydrogen, let's look at a combustion reaction a little more common in our daily lives: butane. Butane is most commonly used as fuel in most lighters, and it is C4H10. And its combustion reaction is this. Butane plus oxygen creates carbon dioxide and water. So the key distinction between this example and the last one is that hydrogen atoms are already bonded with carbon here. As such, the drop in kinetic energy will not be nearly as dramatic as last time. However, we will see a release of energy in the form of photons. In fact, the photons released from this particular reaction are in the visible spectrum, with a wavelength about 420 nanometers, which is why butane emits a dark blue light. Now, I have with me a butane lighter. Make sure it's turned on. And as you can see that very well. Moving on to another common fuel, propane, which is C3H8, and the equation for this combustion reaction is propane plus oxygen comes out with carbon dioxide and water. So you may start to notice a pattern here. We can generalize this to CXHY which leads to XCO2 Y over 2 H2O, where Z is X plus 1/4 Y. Now, of course, you might need to manually balance out the sides of this equation as necessary. So we've looked at hydrogen and the alkanes. Those are the two most common forms of complete combustion. But what other forms of complete combustion are there? Well, we have the alkenes, such as ethylene, propene, and butene, and the alkynes, acetylene, propyne, and butane. Here's an example using ethylene and acetylene, and both of these can be generalized, just like the alkanes. Then there's the alcohol family. An example would be methanol, and this family can also be generalized as well. Finally, there are the sulfates and the sulfides that can react with either oxygen or water. Specifically, sulfur combusts when introduced to oxygen, resulting in sulfur dioxide. Hydrogen sulfide can react with oxygen to form water and sulfur dioxide, and sulfur trioxide can combust when introduced to water to form sulfuric acid, just to name a few. Now clearly, I can't list all possible examples of combustion. These are just some of the most common examples that I was able to find. So that was complete combustion. Now that's probably not the form of combustion that you're most familiar with. Now when we think of combustion, we typically think of a red and orange glowing flame, typically associated with fire. Now this type of combustion occurs when we have incomplete combustion. But what is incomplete combustion? How does it work? So incomplete combustion is a two-step process: pyrolysis and complete combustion. Now you might be wondering why this version is called incomplete combustion if the second step involves complete combustion. The reason for that is because not everything that comes from pyrolysis combusts. Now pyrolysis is the process by which an organic material decomposes into two products: a combustible gas and a highly carbon-based residue called char when introduced to a high temperature. To be clear, this is not combustion. Remember, combustion is, by definition, a rapid exothermic chemical reaction, and pyrolysis lacks all of these elements. First, pyrolysis is actually an endothermic reaction. That is to say, significantly more energy must be put into the system than what comes out. Second, because it's endothermic, it can't create a rapid chain reaction like combustion. Finally, pyrolysis is not a redox reaction. Now we know this because pyrolysis can occur on an organic material even when it's in a vacuum. So there's no oxidant to transfer its electrons onto the organic material. In fact, as I mentioned briefly, pyrolysis is a decomposition reaction, which is one of the 6 classifications of reactions. Now, once pyrolysis occurs in an organic material, what we are left with is a char residue, usually charcoal, and a highly combustible gas, usually either methane or ethylene. Now, once that gas is introduced to oxygen while heated, we have complete combustion, as we already saw before. But that's not the end of the story. As many of you are aware, char materials such as coal, charcoal, tar can be burned further as well. Indeed, this is yet another form of combustion. If we take charcoal, which is primarily carbon atoms, and apply a little activation energy, it combines with oxygen to form carbon monoxide and carbon dioxide. The residue ash, composed of various minerals, is non-combustible, and that's why this overall process is considered to be incomplete. So we just looked at both forms of combustion, but there's still a few aspects of combustion that I want to go over, specifically some of the misconceptions of combustion. Now, one of the misconceptions is that a blue flame burns hotter than a red flame. Now, this is sort of true, but it's really a gross oversimplification. Now, as we saw earlier, the blue flame actually occurs due to electromagnetic radiation. Specifically, when the sigma bond is formed, the electromagnetic repulsion between the electrons causes them to slow down, losing kinetic energy and transferring that kinetic energy into light. Now, that's different from the red glowing flame of a fire. Now, the red glow of a flame is actually due to what's called black body radiation. So if we were to imagine a candle, the wick is glowing at a specific wavelength that's in the visible spectrum that we can see. Think of it this way, in both examples there's radiating light that we can see, but one comes from the actual process of combustion, and the other comes from a result of being heated by combustion. Now, the second misconception I want to talk about has to deal with what's called the fire triangle. Now, if you were in elementary school, you probably were taught this particular triangle. You need 3 components in order to have a fire. Specifically, you need oxygen, fuel, and heat. And that if you don't have any pieces of this triangle, you're not going to have a fire. Now, again, there's some truth to that, but it's really a gross oversimplification, as we've already seen. For one thing, you don't actually need oxygen to have combustion. There are examples of combustion that use a different oxidant other than oxygen. For example, there is zinc and sulfur to create zinc sulfide. Similarly, hydrogen combusts when introduced to chloride. We get hydrogen chloride. Both of these are combustion reactions because they fit our definition of a rapid exothermic redox reaction. Now, there are plenty other alternatives to oxidants other than oxygen to have combustion. Specifically, just to name a few, we have chlorine, fluorine, chlorine fluoride, nitrous oxide, and nitric acid, to name a few. So as you can see, this triangle is a little more than misleading when it seems as though you need to have oxygen to have a combustion reaction to create fire. Now, the third misconception I want to talk about is striking rocks or flint can create a spark and start a fire. Now, funny enough, I actually believed this misconception until Senku specifically addressed this in episode 4.
Finally, pound it down till it's packed solid.
Need a pounded, bro? Cause that sounds like the perfect kind of job for me!
Are you sure that's a good idea? I'm scared if you use all your strength, you could make it spark and go boom, like with flint.
Yeah, no. Hitting stone with stone doesn't actually create any sparks.
Oh, I didn't know that.
Hey, you're right. That's because flint is not your ordinary type of stone. The metal in it is what makes the spark.
So as Senku says, he's absolutely right. Rocks do not create a spark when struck. And the same goes for any two pieces of flint. Now, flint's special in that it's a very strong mineral. In fact, it's one of the strongest minerals that you can find out in the wild. And that's the very reason why it was used as the head of weapons and tools by our ancestors. Now, how you do create a spark is if you have some pyrite, aka fool's gold. So pyrite or iron sulfide is a fairly common mineral. It can be found in most mineral deposits and quarries around the globe. Now, despite its gold color, it is fairly easy to distinguish pyrite from gold. Add to that its global abundance, and it's fairly easy how it's got its nickname, fool's gold. YouTuber NileRed has a really great video that goes over pyrite in much more detail. Link in the description down below. So here's what happens when you take a really strong mineral like flint and strike it against pyrite. What happens is you're using friction to generate heat on the surface of the pyrite, and you're going to actually be ejecting bits of iron off of the flint. So when you see a spark, what's actually happening is you're seeing particles of iron being ejected, super hot and heated, off of the pyrite. And this is what's to create enough heat to help generate a fire. So I have with me some bits of pyrite and flint, and so I'm going to go ahead and try to demonstrate how to create some sparks by striking the pyrite with the flint. So take the sharp edge of the flint, strike it against the pyrite. Let me get better. Oh shit. I don't know if you can see that, but oh, Jesus Christ. Oh shit. I can't really look while I'm doing this, but you can see the soot on my fingers. You can see that. And if you were here, you could smell it. Like, you could smell the smoke or the sparks. But yeah, you could even see like kind of like a soot coming off the flint there. Later on, pyrite was replaced with bars of carbon steel, and flint was still used because of how strong it is to scrape the edges of the steel to generate sparks. Now, steel has since been replaced with something called ferrocium. Now, ferrocium is a complex alloy that's made up of iron, cerium, neodymium, praseodymium, magnesium, and lanthanum. Basically, it's an alloy that was specifically designed to generate as much heat and as many sparks as possible to reduce the difficulties of fire making. So if we scrape off the edge of this ferrocium, we're going to just exponentiate whatever we could get with this pyrite rock. So now I want to finish this episode by going over some of the more practical applications of combustion, specifically how to go about making a fire. Now, if you're out in the wilderness or stuck in a post-apocalyptic stone world like Senku, you have basically two main options available to you. You either can create sparks taking some pyrite and some flint, or you can start rubbing sticks together, which would generate enough friction to generate a fire. Now, since we've already taken a look at the spark method, as I'm going to call it, all that's left to do is to examine the stick-on-stick method, demonstrated by Senku. Let's try it out. So I'm here at a friend's backyard because he has a fire pit, and I don't want to set my house on fire or get arrested by the police for setting the house on fire. So what we're going to do now is we're going to start rubbing, we're going to be based on friction through wood on wood, essentially. Now, I haven't attempted this yet. I don't expect this to actually go very well. There's this really good YouTuber named Mike Boyd who can show you how to do this correctly, and it took him about an hour and a half of attempts to try to get this to go. But we're still going to attempt this just to see how this goes. So yeah, without further ado, we're going to try creating fire through the stick-on-stick method. So we're gonna see how this goes. It's probably not very well. Oh God. Yeah, it's already gonna be a disaster. I can sense it. Maybe I have to twist it more. No, that's not gonna work. The thing is, like, when I move the rope, the stick is not catching, because the whole thing is like by twisting, the stick is supposed to spin. Maybe this will help. Well then, now it's just stuck. No, that's not gonna work. So I know this is possible. How the hell are you supposed to do this? They make it look so easy. Oh, my back. Oh, I'm so hungry. It's like distracting my attempts. I have to re-strategize. Oh. It's so hot out. I haven't eaten like almost all day. Do you give up? Do you just lay down and die? Nay. Behold, fire from the sticks. Is that convincing? You think that was convincing? No. Okay. Oh. That's about going to do it for this episode. If you like what you see, feel free to like the video, comment, and subscribe to the channel for more Science Behind the Dr. Stone episodes. I need a shower.